In this video, we're going to cover section 11.4 on the reactivity of carboxylic acid derivatives. Now, the relative order of reactivity of carboxylic acid derivatives, this is based on their relative electrophilicity. And that's dependent upon the atom or groups of atoms that are directly attached to the carbonyl carbon. And how we can rank these particular derivatives is in somewhat dependent upon the nature of the leaving group. And so the chlorine atom here can leave as a chloride, which is very stable in a weak base. Similarly, if this group were to leave in a reaction, it would leave as a carboxylate, again, a resonance stabilized and fairly weak base. Whereas the two species below, the esters and the amides, these leaving groups, if these groups of atoms were to leave, they would leave as oxides and the amide ion. And these are relatively strong bases. So due to the relative nature of the leaving groups, the reactivity of the species can be determined. And so this is the general order of reactivity, that the acid halides are the most reactive carboxylic acid derivatives. The acid anhydrides are also very reactive, similar in reactivity to the acid chlorides. And then we have less reactive species, the esters and the amides. So what this generally means is that esters and amides, for these species to be reactive, they must undergo reaction conditions that are a little more harsh. One example would be adding heat to a system, or maybe adding a catalyst or a combination of the two. Now, the main difference between the reactivity of these carbonyl-containing compounds relative to what we observe for ketones and aldehydes is that carboxylic acid derivatives have atoms or groups of atoms that can function as a leaving group, whereas in a ketone or an aldehyde, a carbanion as a leaving group or a hydride as a leaving group is very unlikely. And so we don't see the same possibility with ketones and aldehydes as we see with carboxylic acid derivatives. Now, when a nucleophile attacks a carboxylic acid derivative, a reaction can occur in which the nucleophile ends up replacing that leaving group or that group of atoms. We refer to this reaction as nucleophilic acyl substitution. And this is the last mechanism that we'll cover in this course, and is the main mechanism that we observe for carboxylic acid derivatives. Now, this mechanism is carried out in two steps, again using two of the arrow pushing patterns that we learned earlier. It involves nucleophilic attack and loss of the leaving group. And so, different from what we saw for nucleophilic addition involved nucleophilic attack, but the second step was a proton transfer of this tertiary alkoxide intermediate. But for nucleophilic acyl substitution, we have reformation of the carbonyl and loss of the leaving group to give us a new carbonyl-containing compound. So as you can see, we have nucleophilic attack onto the carbonyl carbon, breaking of the carbonyl pi bond, and the formation of a new tetrahedral oxide intermediate. But in the second step, what we observe is reformation of that pi bond between carbon and oxygen and the loss of leaving group. And so that results in an overall change in the group, which is bound to that carbonyl carbon. So we have a substitution reaction occurring. So for all the carboxylic acid derivatives, we're always going to see reformation of the carbonyl and loss of a leaving group. Unlike with aldehydes and ketones, the carbanion or hydride are never formed. And so for aldehydes and ketones, we only observe nucleophilic addition. We don't observe nucleophilic acyl substitution. Now here's one example, converting a acid halide into an ester. And so in this reaction, the nucleophile is an oxide. Here we see methoxide being used. Again, the acid halides are very reactive because of how stable the chlorine atom is as a chloride. And so we see we have nucleophilic attack, break the pi bond, we form our tetrahedral intermediate, our oxide, we have reformation of the pi bond, and we kick out the chlorine atom as a chloride. Reforming, again, our carbonyl, and the net result is a substitution of that original chlorine atom for that incoming nucleophile, the methoxide. And so our net result is the formation of an ester, and as a side product, we've lost the chlorine atom as a chloride. Now it's really important to recognize that in nucleophilic acyl substitution, at the very minimum, these two steps are involved, nucleophilic attack and loss of leaving group. And it's also important to recognize that an intermediate is formed. This is not a concerted mechanism. This is a stepwise mechanism. So in nucleophilic acyl substitution, we do not see the attack of the nucleophile onto the carbonyl carbon and loss of the leaving group occurring in a concerted manner. This is not what we observe experimentally. We must go through the tetrahedral oxide intermediate. So what we will be looking at in the remainder of this section are the specific reactions of each of those carboxylic acid derivatives. And primarily the focus will be on the various reactions that occur via this mechanism of nucleophilic acyl substitution. So if you have any questions about this particular mechanism, by all means, send me an email. Thank you.